Okay, hello everyone. Welcome to today's webinar titled Proper Calculation of the Uncertainty Factors and its Application to the Analytical Evaluation Threshold and for Quantitation, hosted by Biopharma Webinars and presented today by Dr. Dennis Jenke, Chief Executive Scientist at Triad Scientific Solutions. So Dennis, hello, welcome again. Thank you for joining me here today. It's a pleasure to have you as always.
Marcus, it's always a pleasure to be here.
Thank you. And joining us, we also have Dr. Jan Baeten, who is the Scientific Advisor R&D at Nelson Labs Europe. So Jan, hello, welcome as well. Thank you for joining us today. It's a pleasure to have you.
Yeah, pleasure is mine.
Thank you. So my name is Marcus. I'll be today's moderator, and please allow me to introduce our next presenter. So Dr. Jan Baeten received his PhD from the Faculty of Bioscience Engineering at the University of Leuven in 2012. After his academic career as a postdoctoral researcher, he joined Nelson Labs in 2015 as R&D scientist, focusing on innovations in analytical services for the pharmaceutical and medical device industries. Driven by his technical expertise in chromatography and mass spectrometry, Jan works on the development of new analytical solutions, strategies, and data processing flows. In his role of technical advisor, he also gives support to business development. Jan is also active in the structure elucidation team, working on identification of unknowns. Okay, and now please allow me to hand over to our next presenter. So welcome, Jan.
Yes, thank you, Marcus. With the nice introduction or the nice presentation of Dennis, we can now smoothly move over to the next part of this webinar, which will deal with how physical-chemical properties can have an impact on analytical responses and how these are actually correlated. And specifically for this presentation, I'm going to talk about GCMS compounds. So just to give you a brief overview of what I'm going to present. So I will just repeat some of the main quantitation challenges for non-targeted analysis. We have already seen a lot of concepts of uncertainty and protectiveness with the presentation of Dennis. So I will be able to move a bit quicker on this one. And after that, I will tackle some quantitation strategies for compounds for which we don't know the response behavior up front. And for that, we did an exercise on the Nelson Labs GCMS database because we have a lot of compounds for which we do know the relative response factors, and we can correlate them with some physical-chemical properties. So I'm going to talk about some quantitation strategies and specifically how the octanol water coefficient relates to the RF. Next, I will also talk about a broader model with not only the log P value, but also other chemical properties which can be used for predicting RFs. And then I will talk about how the relative response factors vary between chemical classes. And I will, of course, round off with some conclusive thoughts. Okay. So we have seen with the presentation of Dennis, the distinction between the net fishing and the fly fishing. You can do a target analysis where you know what you're going to look for. You can make a calibration curve and use the mathematical relationship between the response and the concentration of the analytes to determine very accurately the concentration of your compounds. But of course, when you're doing screening analysis, you're having maybe hundreds or thousands of compounds in your extracts. So there, such a calibration curve option is often not viable or not practically feasible. So one of the options is to look for surrogates, either passive or active surrogates, like Dennis said. But of course, any way that you're choosing a surrogate RF, the question arises: how accurate is my surrogate choice? So if you choose the wrong surrogate or the wrong value, you might end up with a totally wrong concentration. So we have a quite large uncertainty, or at least a larger uncertainty than the targeted analysis. Okay, so the problem mostly, of course, is not with the compounds with a confirmed ID, because for confirmed IDs, you might have a reference standard, and you might know the relative response, so you can it's best to use this one. But of course, the problem arises when you don't know anything about the structure, or you don't know the response behavior of a compound. And it really depends on how much you know about the structure. So you have the complete unknowns, like Dennis said. The only thing that you can really do is just use the RF mean of a distribution of analytes, adjusted with the UF, and use this to calculate your concentrations, your protective concentrations. Of course, when you do know a structure, the best thing, of course, to do is just purchase this standard and determine its RF. But if that's not feasible for some reason, there are other options, and one of those options is to have to take the RF of a closely related surrogate. Of course, the question arises there: what can be deemed closely related? That's kind of a vague term. So I will address that later on. You can also use prediction models based on some properties of compounds, and use that to predict an RF. So these are actually a bit of the options, like Dennis also has explained. So now let's turn to the concepts of uncertainty and protectiveness. So Dennis already explained the concept of the uncertainty factor. If you have two standards, you inject them with the same two standards with the same concentration. You inject them on your system, and you will not likely not get the same response. So that's the reason why you have variations between responses, and we use the uncertainty factor as a number for the variation in these responses. So the first use is of this uncertainty factor is to correct the AET to just have a lower threshold above which you're going to identify and quantify your compounds in your extracts. And like Dennis said, there's also a secondary use, and that is to calculate projective concentrations, so that at least you know for quantitative toxicological risk assessments that your concentration is not underestimated, but is either accurately or estimated or overestimated. Okay, so how projective is the AET? So suppose in the first case that we would just calculate concentrations with the mean RF, if we have a standard normal distribution of a response factor database, using this RF mean is really the same as saying that we are actually protected for 50% of the population. So that means that 50% of the compounds will have an RF which is greater than the mean RF. But of course, 50% protectiveness will be not enough for toxicological risk assessment. So therefore, we are going to use the mean RF divided by the uncertainty factor. So that's an adjustment of the RF mean. So the question there is how many compounds in the population will have a relative response factor which is higher than this mean divided by the uncertainty factor. And the answer to that is really simple. The mean RF divided by the uncertainty factor, you can substitute the definitions of the uncertainty factor by 1 divided by 1 minus the RSD. You can also substitute the definition of the RSD, and then you will can rearrange this equation to mean that mean divided by the uncertainty factor is exactly equal than mean minus 1 standard deviation. So if we go back indeed to our standard normal distribution, subtracting 1 standard deviation from the mean offers an extra 34% coverage. So in total, an 84.1 protectiveness or coverage. So actually, this means this. If you accept the use of the uncertainty factor to correct the AAT and use the mean RF divided by the uncertainty factor, that gives you an 84% protectiveness, and that's what can be called the 84% rule. Okay, so let's see this 84% rule in action, and we're going to look at the Nelson Labs database, for which we took 2,724 compounds with an established, these are all confirmed IDs with an established relative response factor. We calculated all the statistics like the mean, the median, RSD, and also the UF. The UF is here for this subset. It is 2.27, which is about the typical value for GCMS compounds. And the mean divided by the uncertainty factor is 0.25. If we count the number of compounds in our database which have an RF which is higher than this 0.25, we are actually having a coverage of 84%. So that means indeed that if we use this mean divided by the uncertainty factor, that we have this 84% protectiveness. Now, we have discussed already, or Dennis has laid out the difference between accuracy and protectiveness. So let's also address this. So let's see what would happen if we would just use the mean RF to correct concentrations. We would end up with an accuracy of 77%. So that means that 77% of the compounds will have an accuracy between 50 and 200%. So that's That's quite good, but of course, we will, if we do adopt this approach, we will underestimate 54% of the population. So that is not at all protective. So the really thing to do is to adjust this mean RF by the uncertainty factor. And what we see then is that we will lose accuracy, of course, and we will have a higher overestimation rate. So the protectiveness is 84%. But we also looked at what is the degree of overestimation. And we've expressed this by overestimation by a factor of more than 2, 3, and 5. And we see that at least we are not overestimating too largely. So the number of overestimated compounds by a factor of more than 5 is only 3%. Right. Okay, so now let's turn to some quantitation strategies for compounds for which we do not know the response behavior. So we have looked into our GCMS database for which we have a lot of compounds. We have bought a lot of analytical standards. We have recorded the retention time, all the mass spectral properties, also the relative response factor, of course, but also other properties like the molecular weight, boiling point, also the topical polar surface area, which is the surface area of your polar groups in a molecule. And we have also the octanol water coefficients. Okay, so we have been looking at trends. I'm not going to explain all the details of these graphs. It's just to show that we have investigated a lot of relationships between the RF and the upper graphs on the y-axis, and then retention time, molecular weight, and all the other properties. We have also looked at interrelations between log P and retention time, and so on and so on. But the most interesting thing that we have observed is the relationship between the RF and the log P value. So again, we have here the graph of the raw data. You see in the gray dots is really the original data. So this is a large scatter plot, of course. But just to the red plot is actually a bit of a data reduction in terms that it signifies the moving average of the first. So we sorted the data and we took each time the first 100 compounds and then took the average and then put this to hold a database, and then you get this red plot. And then you can see a very clear or distinct relationship in the fact that molecules with a low log P value, so that means that they will have a high hydrophilicity, they will better dissolve in water than in octanol, are associated with poor responders in GCMS. So compounds with a low relative response factor. I think if you will ask this to any GC expert, I think they will nod at you and say, yes, that's completely logical. So I think this is a great thing, of course. But how can we use this relationship? So the first, the idea that we had is just to divide our semi-volatile organic compound data set into two subsets, so in two domains. And we want to use like a sort of cutoff value of the log p value to discriminate and to see what happens then. Of course, we still want to make use of the concept of the uncertainty and protectiveness and this 84% rule. So for that to be true, the two subdomains have to be also normally distributed in itself. So that's what was the target, and it's that criterion that we use to determine the log p cutoff, and that log p cutoff had to be 2. And you see how it results. So the yellow graph is the log p subdomain, log p smaller than 2. Green is higher, log p higher than 2. And you see really that the RF ranges are shifting in those domains. We have also, of course, determined the statistics of these two subdomains, and we see that the compounds lower than 2 are make out approximately 1/3 of the data set. We established also the mean, the median, the RSD, and UF. The UF being also around this typical value for GCMS being 2. And then we see a clear distinction in the mean RF divided by the uncertainty factor. So you see that for compounds with a log p smaller than 2, that we end up with a value of 0.17. Whereas for the log p higher than 2, we have this 0.35. But in any case, if we would use these mean RF divided by the uncertainty factor of each subset or each domain, we come up with the same protectiveness of more than 84%. So how you could use this information is that that the log p you can establish if you have a structure, you have identified a structure, you know it's you can look up its log p value. It can be either experimentally or calculated, and then you can use determine which domain it belongs to, and you can use this 0.17 or 0.35 to correct the concentrations, and you will end up with a projective approach. Other outcome of this possible outcome of this analysis is that well, log p smaller than 2 means that the compounds will more readily dissolve in polar or semipolar solvents, and log p higher than 2 will more be apolar compounds. So it makes sense if you, for instance, if you have an hexane extract, to standard use this 0.35, whereas for water extracts you may use this 0.17 as a default. Now, what about accuracy and protectiveness? If we would just use the mean RF of each domain, which is not adjusted with the uncertainty factor, we would be very accurate. We would be around 80% accurate for the compounds, but also we will also underestimate a lot of compounds. So therefore, still it is needed to use this uncertainty factor to use this 0.17 and 0.35, and then we become projective, so that means we will also overestimate a lot of concentrations. But again, like the first option, is that we will not overestimate the concentrations by a factor higher than 5. Okay. Okay, so that's it for the log P. We also investigated more parameters than the log P alone. So we have looked also at the retention time, the molecular weight, the boiling point, the topical polar surface area, and of course also the log P. We established a general model for this. We only retained the most significant parameters, which were actually the log P, the retention time, and the topical polar surface area, which was then the optimized model. And well, this model allows you to actually predict RFs. So if you have all these parameters, you have the log P determined. You can also determine the topical polar surface area. Of course, the retention time. Then you can predict the RF. So if you do that, you have a very accurate estimation, and you use the model RF, and when you compare it with the real RF, you will have very accurate concentrations. But because it is a model, you will also still underestimate quite a lot of compounds. So still, this approach is not projective. So therefore, it is still needed to use this uncertainty factor to adjust. The uncertainty factor here is just the uncertainty factor of the whole population of the GCMS compounds of our database, and then you will reach a projectiveness of 90%. Of course, you can use this model only for structures for which you or with correctly identified structures, and because we use the retention time, of course, this model cannot be very transferred between labs, or each one of the labs need to establish this model on its own, but it's actually the general ID that counts. Okay, so then let's have a look at some variations, response factor variations between chemical classes. So this is also often like approached like if you have you don't know the response behavior, just take a surrogate from the same chemical class or something that is structurally related, and use that RF of that compound. Another thing that is sometimes proposed is to choose 3 or 5 surrogates representative for the chemical space of extractables, and use these surrogates for concentration estimations. But again, then the question arises, well, how are these response factors being consistent within these chemical classes, and how would such an approach perform? So for the subset of our GCMS database, we have classified all the compounds in main chemical classes. And of course, there are a number of ways in which you can classify extractables or chemical compounds. But for the exercise now, I just used the very large classes like esters, ethers, alcohols, amides, and so on. And when I classified them, I used the term, although it's not entirely correct, monofunctional compound classes, which means actually, for this presentation, that when something is classified as an ester, it only contains ester functionalities. It can be one ester functionality or two, but only ester functionalities. Okay, let's see at the statistics of this exercise. So we have these large classes: the hydrocarbons, esters, ketones, ethers, alcohols, acids, and the nitrogen-containing compounds. So we have these statistics within each class, and you have what immediately catches the eye is actually that you will have an uncertainty factor, which now is for most classes lower than 2. So that means that actually you're indeed by doing this reducing the uncertainty factor. One exception, of course, is the acids, which have an uncertainty factor of 5.7. Which is not very astonishing because we know that acids, at least when they are not derivatized, are not very good GCMS responders. And then you can see the mean RF divided by the uncertainty factor for all the chemical classes. You see the highest number for the hydrocarbons, the lowest for the acids, and anything else is somewhere in the middle. The fact that the hydrocarbons are the highest is also very logical because they are quite inert compounds and are normally quite good GCMS responders. The same data is also plotted here in this graph. So you can see like these box plots for the monofunctional compound classes. The hydrocarbons have the highest range, the acids have the lowest range, and anything else is somewhere, well, in the middle. I've also plotted the mean RF divided by the uncertainty factor in the orange triangles. So you can see that the first observation was that the uncertainty factor goes down, and we have remember when we have the mean divided by the uncertainty factor of the whole database, that value was 0.25. Here, for most classes, we are having a higher value. So that sounds very interesting at first sight. But of course, when you go a little bit deeper and you can plot some detailed compound classifications, like for the alcohols, you can plot the statistics in the same way, but then for all of the alcohols, which is the green box, and then in function of the number of alcohol groups, so the mono alcohols, the diols, and the trials, and then you see that the trials are much lower. The same for the amines. So we have the primary amines, the secondary and tertiary. The primary ones are having a bit lower RF values than the secondary and the tertiary, which is also not very well. It's quite obvious and logical that this happens. So that also means that if we would just use this the mean RF divided by the uncertainty factor of the whole alcohol class, for instance, which is a quite high value. It's somewhere 0.3 something. If we would use that, then of course we would miss out all of the trials because they will have a much lower response. Also, for the amines, we will we'll miss out part of the primary amines. So that gives you kind of a false sense of protectiveness. The same is actually true for multifunctional compounds. So if you have, for instance, a molecule which contains not only an ester, but also maybe an acid, or you have an alcohol which also contains an ether functionality, and so on. If you allow that, then you can see that the uncertainty factor goes up again, and the mean RF is lower. So that's the same conclusion, is that this gives you kind of a false sense of protectiveness. Okay. Now let's turn to some conclusions. So to achieve protectiveness, the adjustment with the Earth is always necessary. When you do that, that actually means that the AT will be projected for 84% of the compounds. Adjustment of the mean RF with the uncertainty factor will sacrifice some of the accuracy, but at least you're sure that you have concentrations which are not underestimated. The overestimation, as we have seen, is also not higher than a factor of 2 or 3. Then we have visited quite a number of quantitation strategies. So the first one was just the use of the mean RF divided by the uncertainty factor of the whole population. So that's a strategy which can be used for complete unknowns or compounds for which you have a partial structure. So this approach turns out to be projected for 84% of the compounds. And then if you have a known structure, you have better options. I mean, the log P option, or the predictive model, the linear regression model, with the log P being actually the most accurate one, and the linear prediction model being the most projective one. Then on the surrogates based on chemical classes. So it seems that indeed by classifying compounds into large chemical classes, it seems that this is a way to reduce the uncertainty factor to some extent. But of course, when doing so, it's important to remind that it's still needed to have some residual uncertainty factor correction. Still, for this residual variance, it would still the uncertainty factors that we have seen for these chemical classes is not 1. It's 1.6 or something. So you still need correction with the uncertainty factor. And the second thing is also that it gives you a false sense of protectiveness. So we have seen that the number and the type of functional groups still has a large influence on the relative response factor. So this is a risk that the more polar groups will be underestimated, and it's also so that compounds with a lot of polar groups, they're also toxicologically more likely to be active and potentially unsafe. So that's kind of an important caveat there. And of course, it all depends. I mean, now we have used one way of classifying chemicals into large classes. If you do it another way, it might give you potentially another outcome. At least if you if you want to correct with a surrogate which on close structure matching, it's important that you have the same number and type of functional groups because this has the largest influence. Okay, thank you for the presentation, for your attention. And if there are any questions, feel free to ask, and I will give it back to you, Marcus.